Okay, so the first isomorphism theorem tells us that, if I have SU2 over Z2, now what is SU2? SU2 we see is S3. And you can verify that the Z2 that we're looking at is actually the antipodal point, identification of the antipodal points. So if I have, so this is S3, and it's actually the identification of the antipodal points. Okay. So, and this is the equator, which is an S2. Okay. So this is going to be equal to SO3. So that means that, all the points in the northern hemisphere can be identified to antipodal points in the southern hemisphere, except for the equator. On the equator, we have, of course, also the antipodal identification. So I can describe the space topologically as just one hemisphere where the boundary is an S2. Basically, so suppose there's a point number 1 and there's a point number 1 prime, point number 2, point number 2 prime. So these points become only one point here, one.
So it's a 2-disk?
It's a 3-disk. It's actually not a 3-disk because it's a 3-dimensional disk, but since we are taking the, but we cannot, but we are taking the whole of the equator has opposite points identified. Okay, so this point is identified to that point. This point is identified with this point. So, and then this point is identified. Okay, so we have a 3-dimensional disk-like thing, but with its boundary is an S2 where the opposite points are identified, where the antipodal points are identified. Okay. So topologically, this is what SO3 is.
So in the right-hand figure where you drew 1, it's basically both 1 and 1 prime identified in one point.
Exactly. Yeah. Okay. All right. So now let's look at this kind of space. Now, if I have a loop like that, now this loop I can continuously deform to a point, right? Right? Because if it's a rubber band, it can be like, suppose a rubber band with a very strong tension, then it'll become very small, right? So now any loop like that can be continuously deformed to a point. Do you agree?
Yes, sir. So there's no like unusual identifications here.
Yeah. However, if I have a loop which starts from here and goes and ends at the antipodal point, that loop, if I want to shrink it down to a point, what would I have to do? I would have to bring these two endpoints close together, right? And if I bring this over here, what happens is this guy goes in the opposite direction. So this loop is an example of a loop that cannot be reduced to a point in a continuous fashion.
Because they have to be antipodal to each other the entire time.
Exactly, because this point and this point are the same point, right? So if you want to bring them together, it's impossible to bring them together because they're by definition antipodal, right? However, on the other hand, if you have a loop which is coming out, say, from here, going here, then that loop will come out here and go here, right? The blue loop. Now, the blue loop, if you bring these 2 points close to each other, then these 2 points will also come close to each other. And the blue loop can become a loop like that, and then we can deform it into a point. So this shows that only loops which go around once to the boundary are non-contractible. If the loop goes around twice, then it's contractible. If the loop goes around 3 times, then it'll be non-contractible again. Okay. So there are 2 classes of loops. Okay. Contractible and non-contractible. So this actually can be converted. This structure of the loop can be converted to an abelian group. I won't go into that, but at least intuitively what happens is that if you have 2 loops like this one and this one, and they share, you can associate with this a group element alpha, and the composition of the group element means that you are going, that your alpha times b means that you first go around beta and then you go around alpha. And so the thing is that, and there you can give a group structure to this sort of, space of loops on a manifold. And that group is called pi1. It's called pi1. It's called the fundamental group, the fundamental homotopy group. And for the pi1 of SO3 is equal to, of course, pi1 of SU2 over Z2. And there's a theorem in homotopy theory where you can relate such a quotient. If the argument of the space is a quotient space, you can relate that to the pi1 lower 0 of Z2. And this is actually means that this is actually Z2 itself. Okay. So the fundamental homotopic group of SO3 is Z2. Whereas on the other hand, pi1 of SU2 is just a sphere. Any loop on the sphere can be continuously deformed to a point. So the fundamental group of SU2 is just the identity, right? So that means that topologically these 2 spaces are different. SU2 is simply connected. SO3 is multiply connected. Okay, I've gone over time, so let me take a break and let's meet back here at 6:20, okay?
Okay, sir.
Okay, welcome back. So before we move on, I mean, let me give you a few, some idea about homotopy groups, okay? So it's not going to be rigorous, but what are homotopy groups? Okay, so these are equivalence classes of maps from SNs to some manifold. It doesn't have to be a manifold, some kind of space, but so if you have some space, say M, and you consider the class of maps from Sn to M, and such that their equivalence classes under continuous deformation. Okay, so the so for example, if I have two maps F1, say from Sn to M, another map F2, which is also a map from Sn to M, but if there exists, say, some other map F, which has some parameter T, such that F of 0, we get the map number 1, and by a continuous deformation of this parameter, I go from map number 1 to map number 2, then they are considered equivalent. Okay, then F1 is considered, small f1. Small f1 is considered equivalent to f2. I'm not so much concerned about the rigorous definition, but let me give you an example. An example is, say, pi1. These are the maps from equivalence class of maps from S1 to some space M. So suppose that our space is some space like this, where there are two holes. So the holes are not part of the space. Now, I have a circle here, and from the circle, I can have many different kinds of maps, right? So I can have a map to a point, right? That's a trivial map. Now, this map could have been anywhere in this space. And these are all equivalent because we can continuously deform this map to go to the other map. Okay, so all these maps are equivalent. Okay, so there's an equivalence class of, and that is going to be an element in pi1. But there's another map, say, which takes the circle to a circle around this hole. And it goes in that way. Okay, so that map, there is no continuous deformation of that map, say, to this map, right? There is no continuous deformation. However, this map is continuously deformable, say, to this map. Okay, so again, there is another map which maps the circle to a circle to a map around this hole. Now, this blue map, this blue circle cannot be the map that takes us from the circle to this blue circle cannot be continuously deformed into a map that goes from the circle to the green circle. So they are inequivalent. They belong to inequivalent classes. Similarly, there is a map which takes us from the circle to another loop which winds around the hole in, say, more than one revolutions. So that map is different from the map that winds around the hole in one revolution. So these maps are, so we see that the maps that take us from the circle to the loops around, say, this hole, they are classified by integers. That integer is telling us how many times the map winds around the hole. So that is, those maps are characterized by an integer, and that integer is called the winding number. And the winding number is positive if, say, it's going in the counterclockwise direction. It's negative, it's going in the clockwise direction. Okay. So basically, this is what a homotopy group measures. Homotopy group measures classes of maps which are equivalent to each other under continuous deformation. And the interesting thing about SO3 is that there are only two types of maps: the maps which are, which can be shrunk down to a point, and maps which cannot be shrunk down to a point. So they together they form a Z2 group. Okay. So that was a very, very hand waving explanation of homotopy group. Okay, are there any questions?
Sir, for the specific case that you showed, will the homotopy group be like Z direct sum Z in that case?
In the case, yes.
Okay.
This would be Z cross Z. Yeah, very good. Yeah, because if I have, say, a map like this, circle like this, I can write this as two circles, one circle going out like this, another circle going like this, right? So I can compose that in terms of two elements in these two different Zs. Yeah.
Sir.
Yeah.
If SO3 has a fundamental group of Z2 that's isomorphic to Z2, does that mean that it has two holes?
No. So this guy has two holes. SO3 doesn't have any holes. It's just not a simply connected space.
I see. Okay.
Yeah. It's like, it's like torus, right? A torus doesn't have any holes, right? In that sense.
Yeah, I mean, I thought it had some higher dimensional holes, I guess.
I mean, you can think of this as a hole, but the better way of thinking of torus is to think of it as a square where the opposite ends are identified, right?
Oh, yeah.
Right. So, I mean, yeah, it depends on what you mean by hole. It does have a hole, but it's kind of.
So toruses also have two distinct equivalence classes, right? Like one along the winding with the pipe, and another going within. Two kinds of paths possible, independently.
Yeah, but torus has many. You can have as many winding in this direction as you want, right?
So it's like Z plus Z again.
Yeah. The thing is that two spaces, if they have the same fundamental, if they have the same topological, suppose you have two spaces, say M1 and M2. And they have some topological invariant, say T1, and this one has some topological invariant T1, and suppose they're the same. That does not mean that M1 and M2 are topologically equivalent. There might be another topological invariant, say T2, where this is not equals to, they are not equal for the, if you can find two topological invariants which are different for these two spaces, then they're topologically different, right?
Yeah, understood.
Sorry?
Yeah, I understand.
Yeah. Okay, so let's carry on. So the thing that I want you to do as an exercise is the following. To show that the identification of U with minus of U of SU2 results in the identification of the antipodal points of S3. Okay, so this is not very difficult, but you have to think about it.